So in the last video, we took a look at examples 2 and 3, and we saw that we had these kind of different instances where maybe direct substitution wouldn't be able to be used. And we can kind of summarize all of these ideas down here in this box. Now, this isn't a perfect set of strategies here. This isn't a great step-by-step process, but it kind of loosely works. It can help at least loosely structure our thinking. And these are strategies for evaluating limits of the form of something over something, whether that's something like 1 over an x squared or something more complicated like what we saw in example 2. Now, we can see here that typically our first step is to try to plug in the value of a. And if we get a real number, then obviously that's our answer. Again, this is specifically if we have a rational function of this particular form. If the limit of the numerator and the denominator is 0, then we might be able to simplify. And if we can't plug in and we can't really simplify, then we could check to see if the limit approaches infinity, maybe by checking the limit from both sides or taking a graphical approach. So we're going to go ahead and try to think through here how we can apply this to some of the other questions that we have in this section. One thing we should note, though, is that this strategy is not perfect. Sometimes in strategy 2, when we algebraically simplify something, we still won't get an answer, and we may have to jump to something like a step 3. But let's try to figure out maybe something like example number 4 and try to see how we can work through this. Okay, let's take a look here at example number 4. We should notice something immediately. Is this a polynomial function that we're taking the limit of? No, because remember that a polynomial function only can have x's raised to powers, whole number powers, and added and subtracted together. That's it. Those are the only options. And so here, I have a square root, I have a division sign, I have x's on top and the bottom. Is this a rational function? Well, again, the answer there should be no, because I have a square root, and square roots are not a part of polynomials. And rational functions are supposed to be polynomials divided by other polynomials. So I should note right away this is not a polynomial and not rational, which means I'm actually not even allowed to try step number 1. I can't plug in. I can only direct substitute if I have a nice polynomial. So what I'm going to be left with here is using my limit laws to try to help me. Now here's one problem though. One of my limit laws states that I could do the limit of the top and the limit of the bottom. But can you tell what I'm going to get for the limit of the bottom? Well, yeah, you could probably tell right away that, oh, I'm going to end up with 0 down there. Notice you could actually see in the numerator that there is a way to use limit laws. Remember that with radicals, and I'll scroll back up to see this, you can actually have the limit move to the inside of the radical and then just apply the radical after you've computed the answer. So that's great. Notice here, if I was to do that, if I did the limit of the inside, x plus 2, that's a polynomial, and I would get 9. Square root of 9 is 3. 3 minus 3 is 0. So I kind of have this 0 over a 0, which doesn't tell me anything, except that I might be able to simplify. So let's think about how we could do that. So I'll start by saying we calculate that the limit as x approaches 7, the square root of x plus 2 minus 3 times x minus 7, over x minus 7. Now how in the world can I simplify this? Like what in the world am I going to be able to do here? And this is actually a perfect time to bring up a topic that we talked about in the skills check videos. Well, what we can do here is we could actually attempt to rationalize the numerator. That is, we could attempt to multiply by the conjugate square root of x plus 2 plus 3. And we'll multiply that on top and on bottom, so we're multiplying by just a fancy version of the number 1. Notice that if we do this, in the numerator, I can simplify my result to look like x plus 2 minus 9. That's what happens here if I distribute everything through. I'm just using difference of squares to do that very quickly. In the denominator, I'm again not going to bother multiplying this out since it's going to be really, really ugly, but I'll just write these two pieces sitting next to each other. Of course, what I'll notice is that that numerator actually does simplify down to just be x minus 7. And so very, very conveniently, we're going to be able to cancel out that common factor from the top and the bottom of this fraction. Okay, so if I go ahead and I cancel that out, I'm just going to be left with a limit as x approaches 7 of 1 on top, and in the denominator I just have x plus 2 under the radical and then a plus 3. Well, now notice I can actually use my limit laws very successfully. I can do the limit of the top and the limit of the bottom individually. If I do the limit of the top, I just get 1. If I do the limit of the bottom, notice I can separate the limit across the plus sign. I can do the limit of the square root and the limit of the 3. The limit of the 3 is just 3, and when I do the limit of the square root, remember that I can rewrite that as a limit of the inside of the square root and then square root after. Oh, and here's a great moment. X plus 2 is actually just a polynomial, so I can direct substitute. So that means I can get 1 over square root of 9 plus 3. That's 1 over 3 plus 3, so that's 1 over 6. So I have a lot of work here. That's a lot of tinkering around, but we see the skills check ideas coming into play. That one way I might be able to simplify something is by multiplying by a conjugate. And that works especially well when I have complicated radicals. Well, now we're going to take a look at example number 5 and try to figure out how could I explain why the limit of the tangent of x does not exist. Oof. All right, for here, I'm going to need to know a couple things associated with some trig. So let's take a look at what we have. One of the first things that we might notice here is that we can't direct substitute. Oops, that is not a good sentence. We notice that we cannot direct substitute. So we notice that we cannot direct substitute since tangent of x is a trig function. So it is not a rational function, it's not a polynomial. So the only other thing I could do is to try to look at the picture of the tangent function, which is a graphical approach, or I could try to check the limit from both sides, like we did when we were looking at 1 over x squared a couple videos back. So I'll state here that we will check the limit from both sides. Now this, of course, is going to require that we understand some stuff about trig, and that we also understand some stuff not only just about like the tangent function, but also about the unit circle more generally. So let's take a look here at how this would play out. I'm going to see that I'm going to have a limit as x approaches pi over 2 from the left, and I'm also going to have a limit as x approaches pi over 2 from the right. Now, one thing that might be helpful here in trying to determine this limit is to keep in mind that the tangent function is actually just the same thing as the sine function being divided by the cosine function. So I'm going to go ahead and rewrite that here for both of these individual parts. It's the sine of x over the cosine of x. Okay, so if I have this, now I can start to think, kind of like what we did before. I can think in these kind of arrow arguments. I'm not going to state what the top and the bottom are, but rather what the top and the bottom of these fractions are going to be moving towards. So let's quickly think here. Sine, as the inside moves towards pi over 2. Well, if I think about this, I think about what I know about the sine function, Think about what I know about the unit circle. I know that in the unit circle, as I move towards pi over 2 from below, that would be like kind of moving this way around the circle, moving towards the angle pi over 2. And so that kind of corresponds to this first limit. And as the sine moves, or as I'm dealing with my angle moving there, remember the sine is going to be tracking the y coordinates of points on my circle. So when I get up to the top, it looks like this would be making the sine move towards the value of 1. I can also see the same thing happens even when I approach the other way. If I approach pi over 2 from the other direction, that is from bigger angles, I'm still going to end up with that my sine is approaching 1. But what is the cosine approaching? Remember, cosine would represent the x-coordinates of points on my unit circle. So my x-coordinates here are both approaching 0. Notice on the red arrow, the x-coordinates are getting closer to 0, but are always positive. And on the blue arrow, they're approaching 0, but are always negative. And so I can communicate this by writing, over here, the bottom's going to be moving towards 0, but will always be to the right side of 0. It'll always be bigger than 0. Over here, I'm going to get the values are going to be moving towards 0, but always smaller. And now I can think about what the result of this is. What happens if I take a value like 1 and I divide it by a number that's a little bit to the right of 0? Well, again, you can always experiment with this on a calculator, but we can see that's going to create infinite. What happens when I take 1 and I divide by a number close to 0 that's negative? Well, there I'm going to have a positive number over a negative number. That's going to give me a negative infinite value. And I got it. Well, notice then overall, what does this tell me about the limit as x approaches pi over 2 on just the regular old tangent function? If on the left side I get infinite, and on the right side I get negative infinite, what would I say happens from both sides? Well, I would say that this limit does not exist. And I got it. You could actually take a look at a picture of the tangent function to again also see this same sort of behavior.